Hello, my name is Tara El Sabi, and I'll now be presenting my project for the course EEC 442 Communication Systems. And this project explores key concepts in modern communication, which include sampling, quantization, source coding, source coding and decoding, channel coding and decoding, modulation, demodulation, noise analysis, and detection. So let's start off. First of all, I started with sampling and reconstruction. And so sampling and reconstruction is basically converting continuous time signal into a discrete time signal by capturing values at specific intervals. And we wish to reconstruct the original continuous signal from its sampled version. And all of this whole process has to adhere to the Nyquist sampling theorem, which means that the sampling frequency must be at least twice the max frequency. And so for this part, I used three sampling rates: FFS over 2, FFS over 4, FFS over 8, FFS over 2 being the Nyquist rate. And obviously, uh, the expected output is if I pass in a audio file, the lower we go, the more distorted it will be. And let's listen.
EECE 442 test test 123.
That's the original. And now
EECE 442
FFS over 2.
test 123. EECE 442 test 123. EECE 442 test 123.
Now, as expected, the sound at FFS over 2 or the Nyquist rate was nearly indistinguishable, while for the lowest frequency rate at FFS over 8, the sound became heavily distorted, and we can see that through these visual representations here. The sampling at Nyquist rate is almost identical, while that at FFS over 8 becomes heavily distorted, especially at the region, at the borders, I mean. Now moving on to the second part, which is quantization. And quantization is just the process of mapping a continuous range of amplitudes to a finite set of levels. So a continuous range of amplitudes being our voice note. And our goal here was to just analyze how the bitrate affects the accuracy of signal representation. And we measured this using mean squared error. And we also measured the SNR, which is the signal to noise ratio, just to analyze the impact of the quantization levels. Now, as for the results, first of all, the our bit rates that were chosen were 2, 4, and 8. And as for the results, which haven't loaded yet graphically because the computer is slow, so we will look here where you can see that, one second, you can see that uniform quantization for low bits gave us a high mean squared error, and as we moved up in bits from 4 to 8, our mean squared error decreased with 8 having the lowest. However, when we did the non-uniform low rate quantization, I forgot to mention that we're working with uniform and non-uniform quantization. Uniform being dividing the amplitude range into equally spaced levels, while non-uniform is thresholding the levels based on the signal's probability density function. And so for the non-uniform 4 bits, we actually achieved a lower uh, mean squared error than the 4 bits using a uniform quantization. And I also tested out the signal to noise ratio for only uniform quantization, and I got that as we increased the bits, we had a higher SNR ratio in decibels, of course. Moving on to the third part, wait, let me just check if yep. As you can see here, there are visual representations of MSE versus bitrate decreasing and reaching almost a minimum at 8, and SNR increasing linearly between 2 and 8 bits. For the next part, we'll be talking about source coding and decoding. So, source decoding and decoding. Of course, we illustrated we're using two approaches, fixed length coding and Huffman coding. Now, source coding is just reducing the redundancy in signal representation for efficient storage or transmission, as we learned in class. Fixed length coding means we have no prior knowledge of the of the signal's probability distribution. While for Huffman coding, we get shorter schemes just because we leverage that signal's distribution to achieve a better compression. Now, as for the results, for our 2 bits, one second. Uniform quantization for 2 bits, we had an average code word length of 1.5, entropy 1.5, which is obvious they have to be equal because it's uniform, while the Huffman had a lower entropy and average code word length, 0.6, 1.1, compression efficiency of 27%. It effectively reduced the redundancy, but the limited number of levels just constrained our compression. For the 4 bits, you even had the higher average code word length entropy, obviously, because the more we increase the bits, the more the average code word length is going to increase, as well as the entropy. Where did we disappear to? Okay, and uniform quantization at 8 bits, we had the highest average code word length, 7.9, and for the Huffman, 4.1, 4.2, and note that these values have to be close to each other. The closer they are, the better, especially for Huffman. And they're always going to be equal to each other in the fixed length coding. Now for the non-uniform distribution, I tried out one case for 4 bits and these were my results. I got actually the highest compression rate, surprisingly, and the entropy 1.2, 1.5 as compared to here, 4 bits, which was 1.4, 1.6. Now, this model illustrated the effectiveness actually of Huffman coding and reducing redundancy for both uniform and non-uniform quantization. This highlights the importance of leveraging signal characteristics to optimize compression, and actually the Huffman coding emerged as the most efficient approach here. Now, moving on to our fourth module, which is channel coding and decoding. And this is a key technique used to ensure data integrity over noise channels, and two approaches were used. So if you go down here, two approaches were used, first being Hamming 7.4 and second one being repetition coding. Now Hamming 7.4 is a block coding method that encodes 4 bits of data into a 7-bit code word by using parity bits. And repetition coding is a simple error correction technique where each bit is repeated multiple times. In this case, we picked 3. And decoding works by using majority to decide, original bits. Now we used a bit error rate of 0.05 for predefined channel error probability. And here our results are as follows. So if you go down here, for the Hamming 7.4 we tested with 16 bits, 0.05. We got 2-bit errors after decoding with a bit error rate of 0.12. Repetition coding, usually for the most part, it's always between 1 and 2. Majority of the time it's 1, 0, and it's 0.06. Repetition coding, total bits tested 16, same error. We had a bit error of 1. Majority of the time it's actually 0. Surprisingly, this is almost the first time I see it with 1, bit error rate 0.06. And we can conclude here that the Hamming 7.4 is a compact and practical solution, but struggles with higher error probabilities, and repetition coding is highly reliable, but the problem is that it uses significant bandwidth due to the fact that it depends on the number of repetitions. So the higher number of repetitions you have, the more bandwidth it's gonna use. But all in all, both methods effectively reduced the bit error rate compared to the row channel. And moving on to the final section, not the, before the final section, part 5, modulation, demodulation. This is a fundamental process for transmitting data over physical channels. So we analyzed three different schemes: BPSK, which is binary phase shift keying; QPSK, which is quadrature amplitude modulation; quadrature phase shift keying; and then 16 CAM, which is 16 quadrature amplitude modulation. The simplest one being BPSK just uses two constellation points representing 0 or 1, then QPSK uses 4 to encode 2 bits per symbol, and finally the 16 CAM, as you can see here, uses combines amplitudes and phase modulation to encode 4 bits per symbol. Now I won't go over the steps because you don't have much time, but the results here show that BPSK had an accuracy of 100% and it demonstrated perfect performance due to its high noise immunity and simple constellation with widely spaced points. QPSK accuracy 99.9. Its range is always between 99 and 100, and this achieved this perfect accuracy thanks to its balanced constellation design and moderate spacing points. Uh, And finally, for the 16 cam, we had an accuracy of 75.8, and this reduced accuracy highlights actually the trade-off between higher spectral efficiency and lower noise immunity, making the 16 cam more susceptible to noise and causing symbol errors. Now, moreover, I even tried to visualize a pulse-shaped BPSK signal here using a raised cosine filter, which we learned in class, and this shows smooth transitions between symbols and demonstrates effective pulse shaping. Now for the final part, one more thing, I visualized the constellations. As we can see here, the first one shows the blue symbols aligned almost perfectly with the two ideal points in red, while the final one here, our received symbols in green exhibit significant scattering around the ideal points, which in purple. And this just shows that we have a lot of points deviating far away from their intended locations. Finally, for channel noise and detection, we analyze the impact of noise and channel characteristics on communication systems. And of course, again, we focused on the BER bit error rate. And we used the two common channel models, first being the AWGN, which we learned in class, additive white Gaussian noise channel, which just models noise as a Gaussian process. And then the second one being the Rayleigh fading channel, which simulates more challenging conditions compared to AWGN, which I found this online and thought it would be suitable to use here. And so our bit error rate was evaluated under two configurations, first being the uncoded BPSK where no correction was applied, and coded BPSK where Hamming 7.4 coding was applied, as you can see here. Where is it? Coded BPSK, we used Hamming code here, Rayleigh fading channel uncoded, coded BPSK, and uncoded AWGN. Okay, so the results here showed that here, our output. As you can see, the bit error rate for the AWGN uncoded bit error rate decreased exponentially with increasing EB over N0, which is the energy per bit to noise power spectral density ratio. And we achieved near zero errors at high SNR, while for the coded BER and the AWGN channel, which is this line right here, the BER reduces significantly compared to the uncoded case due to Hamming's coding error correction capability. Now for the Rayleigh channel, actually, the BR performance is far worse than the AWGN channel due to its fading effects, which cause significant signal amplitude variations. And so at high energy per bit to noise power spectral density ratio, fading still introduces more errors than noise alone, and that's a problem. And so we can conclude by saying that this model demonstrates a critical role of channel characteristics and error correction, and ham encoding effectively reduces BER, as we can see with this line here, but it's actually limited in challenging Rayleigh channels. And so moving on with our final thoughts, we explored key components of digital communication systems, from sampling to quantization to coding to modulation, and finally choice, channel and noise analysis. And regarding future work, while reflecting on these results, we can move on to you can extend to involve multi-antenna systems like massive MIMO. These are helpful in 5G and 6G generation operations. We can incorporate terahertz communication simulations. And finally, we can also use machine learning, which prevents another avenue for innovation. Also, finally, I'd want to conclude by I read the contemporary research topics and joint communication and sensing, non-orthogonal multiple access and THE systems. This project can actually contribute to the rapidly evolving landscape of 6G technologies, since, for instance, the convergence of THC communication and sensing could actually enable applications requiring ultra high precision and massive connectivity. Thank you.